And now let's go to the heat equation. The heat equation is similar, except now we need two derivatives. So let's come down to our derivative matrix here. And now we're going to have two derivatives. And that matrix looks like the following. One's on the corners. 1, -2, 1 on the diagonals and off diagonals. Okay? So that's a very simple change. Your matrix A just gets changed a bit. Come back up here. Your CFL now picks up the most important thing of all. Remember, that was all you cared about last Friday, was that delta x squared on the bottom. Perhaps you forgot that you were so fixated on that last Friday. Delta x squared now, CFL. Okay, so we can still do all the same things here. You know, we get CFL, blah, blah, blah. Let's go ahead and just do, we're going to do here, start off with forward Euler. So we define an initial condition U naught. We save it. We have our CFL condition. And by the way, for right now, let's just check out what our CFL is. 0.05. So remember, we were doing something like 0.2 before. To do that. CFL of 20. Dang. We have to get it under a half, right? All right. How do we do that? Well, here's one thing you could do. Change n to 100. Like, it's one thing you can just keep taking the delta t smaller, or you could take, you know, n to 100 is going to make your delta x twice as big. So down to 5, factor of 4, which you knew would happen. Then you could say, okay, I need another factor of 5, so let's bring this down to, I think that's right, 1. Oh, actually, we need to get it to below a half, right? All right, fine. See, that's costing me 0.02. I was way up at 0.1 and stuff with the wave equation, and now that gets me at a half. So I have my CFL defined. I go ahead and I have my initial conditions. I have my second derivative matrix, and now we come to the heart of the code right there. So first of all, let's go ahead and comment out our leapfrog method. Let's go ahead and just do our, and here's the only line of code we need to play with for the second derivative. My point in the future, U1, is what it is right now, plus, in this case, what we had was, it's just CFL times A times U naught. Yeah, there it is. That's it. Not much change. The matrix A looks quite a bit different.
Length t minus 1 now?
Yes, and length t minus 1. Okay, so you see, really, I mean, even if you look at this code, we just went back to almost basically the same line of code we had before for leapfrog. The difference is that matrix A has a very different structure, and there was a factor of a half, but still, the big difference here, this line of code is the same. Just that A now tells me how I relate to neighbors differently. A now tells me -2 of myself, 1 of my neighbors, whereas before I was 1 of that guy, -1 of the other guy. Go through, plot. Okay? So let's go ahead, run this thing. Oh, do I have a break? I do have a break. Okay. Run. Okay. Here it is. Now, you see that? It's, see how much it's, there's a lot of points here. If you remember, I'm taking 0.02 now, so, and I'm running at 4 units, so there's a lot of data here. So you might want to control how much data you have out to the system. But right now, fine. It's, this is okay. Let's just run it for a little shorter time. In fact, we're going to want to do that anyway here, because you'll see why. Let's run it out to 0.2. Okay, still a lot of data, and you know we're not going to spend time managing that data very much. But there you go. It's a diffusion problem, and what it is is just this Gaussian just starts to spread out. So like you think about it as the heat equation is like if you put some hot temperature here, typically the way it's introduced in a class, you say, consider a slender rod which you heat it somewhere, and then you ask how does the temperature, you know, if you heat it up at one spot, how does that heat spread throughout this rod? And then here's what would happen. This would cool down, and the heat would diffuse into the other areas. And then eventually the heat would just dissipate away to zero. So if you let this run long enough, it goes to zero. Okay, so there you go. This has a CFL. That's actually correct, stable. So if I kept cutting the delta T in half, I'd get the same thing. Now, let's go ahead and violate the CFL. So for the Euler method, I'm just going to do the following. I'm going to make it 0.04. So now my CFL is 1 instead of half. Now if I run this thing, oh, 10 to the 9. So if you were to light this slender rod in the middle with a Bic lighter, it would blow up. It would melt everybody around you and the whole planet because you generate heats of 10 to the 9. So don't do that with a Bic lighter. Okay? So you can see this is exactly what happens. You just do a little delta T, boom, this thing just takes off on you. By the way, that's just in 2 units. You run this for 10, this is like 10 to the 200th power. Okay? Total garbage. So, like I said, this is what I mean by this. When you violate CFL, it usually announces itself to you. Right? It says, you do not expect that when you put a little bit of heat into a system with maximum amplitude of 1. So first of all, if it's a linear system, you don't expect it to get hotter. Second of all, you certainly don't expect to get so hot like 10 to the 9. Totally bogus. So right away you can start saying, okay, there's just something wrong here. Start cutting your delta T down. In this case, you can cut the delta T down, and once you get it below what we had there, 0.02, you keep cutting it down, you get the same idea, physics out every time. So it's just, okay, I've done the conversion study, I know it works. And in this case, we can actually do it explicitly. Okay, so that's what happens. Now let's go ahead and go to the leapfrog method with this thing. And I'm only going to run it out here to 1. And in the leapfrog method, all we're going to do is, we're just going to use the same initial conditions for both time 0 and time 1. Just because it's like super easy to do. For no other reason. And then I'm going to come here, I'm going to basically comment that out and uncomment this. So for the leapfrog, here it is. And what it says, leapfrog has a factor of 2 in front. So you put this. The future is what it was one time ago, plus a little bit of the present. Update everything, write it all out, T minus 2, and we can go to town. That's it. Go. Ooh. See that? That's 10 to the 14 now. Okay? That's 5 orders of magnitude worse if you use leapfrog. In fact, leapfrog will never work. We know that for this equation. So again, you can see, there you go. That's violation of CFLs. Okay? Lights on, I guess. Up front. Awesome. Okay. So to finish off, let's just really briefly talk. In these 2 equations, right, I know how to make them work. I can do the full CFL. And what we did today is really say we knew exactly where the CFL boundaries were to make these things work or not work. In practice, you're not going to know this. I mean, this is right to your point, Charles, which is you don't know it in practice. You have an equation, supposed to have some nonlinear terms, have some stuff in there. I can't do a von Neumann analysis. What you can do is change your delta T. And what you can do is say, I want to fix, so again, I made this point earlier, fix your spatial discretization that you want to get the error you'd like. Right? So you suppose I want errors of like 10 to minus 2, 10 to minus 3. Well, then pick your dx to make this happen for you. So for instance, if you pick If you want error of like 10 to minus 4, you'd pick your dx to be about 10 to minus 2. And you say, okay, that's what I want for my error. And now what you do is just pick a dt, and you start walking it down. Cut it in half, cut it in half, cut it in half. Once you've got the solution to converge, in other words, I cut the delta t in half, and it's giving me the same thing. Cut the delta t in half again, still really giving me the same thing, right? Typically, the way you might think about this is you take delta t to be super, super small. That is your exact solution, okay? And then you should take your delta t's, keep cutting them in half, and it should be converging to that, okay? And if it's not, that means something's wrong. Generically, things are not going to be like these two equations where if you apply Euler here, it always is unstable for no matter how you pick delta t. Generically, that's a result that's confined to these very simple equations. If I have nonlinearities and other stuff going on here, there's always going to be some lambda that will probably make it work. Same thing here. It's not like Leapfrog's always unstable. Very few schemes are always unstable. Only in the simplest cases can you always say things like it's always unstable or always stable. Generically, it's always going to be, there's a range that works. Drop it below that range, you're fine.
So if you're testing convergence, you can change your CFL by increasing delta x size, right, or reducing delta t. Is there offer a reason with making your problem to make delta x coarser because you want to test convergence faster?
Yeah, so a very nice thing to do is you can always make delta x bigger, right? Because the scheme is independent of what you're saying about accuracy, right? The scheme is. So if you want to test it more quickly, yeah, you pick your delta x to be, bigger, so you don't have to do as much work, right? And because everything's constrained by this ratio of delta t over delta x. So for instance, even if you pick delta x to be 1, right? You're not making a statement about the accuracy of what you're getting. You're making a statement about the stability of the scheme. Then once you establish stability of the scheme, then you can go back and say, okay, now let me crank down the accuracy. Yes. Yeah.
Is there a way to automate picking of delta t to get convergence?
What's that?
Is there a way to automate picking delta t to get convergence?
Yes. So a lot of the adaptive steppers, they basically have an algorithm that does the following. They say, look, let me take a delta t, and I will calculate what I get from one step. So this is how adaptive steppers work. Take a delta t, run delta t into the future, ask what is the solution here. Now, do the same thing again, but cut your delta t in half, so you have to take 2 steps over here. And ask, now I have this solution, what is the difference between this solution and the one I had previously? If that difference is less than 10 to the minus whatever, 6, you say, oh, great, I can pick that delta t. In fact, adaptive stepper will say, whoa, that worked. How about if I take 2 delta t? Let me see if I can take a bigger step. Then it starts taking big steps. It tries to take as big as it can. Right? And what it's looking for is the difference between delta t and half the delta t to be less than 10 to the minus 6. And then it says, okay, I've got it. You can do the same thing here. Keep automating until the answer you get from taking delta t and delta t over 2, the difference between those two solutions are less than some tolerance that you specify. And once that's achieved, that's what it'll pick its delta t to be. And by the way, adaptive stepping does that every single time step. Because sometimes a solution will start changing rapidly, right? Solution's moving along, then it makes a transition. Well, you can't take the same delta t when it's making a rapid transition. You can't take that same delta t that you were using over here. You have to take a new delta t. So it always is adjusting its delta t as it goes along. Always asking the question, can I take a bigger step? Do I have to take a smaller step? Okay. All right. Anything else? We're ready for this week? Are you guys ready for this week? It's Monday. A little bit chill. I know. Everybody's, how's your stamina? You guys okay? Getting through the quarter? All right. Sensing a little bit of, that mid-quarter, I don't know what to call it, blues. Start playing some B.B. King up here later. You guys have a good Monday. See you Wednesday.